Okay, so we have started to stream. I'm also starting to record. Okay, just for the just for everyone to note. Okay, so we have started to stream and it's also recording. Let's get this session started. Okay, I hope my whiteboard is visible to everyone.
Yes, sir.
Okay, super. So we are continuing discussions on week 4, and maybe week 5 will also be touched upon today. So in week 4 and week 5, we are basically looking at modeling, right? Modeling a data, and we were looking at the demand response curve, which is nothing but d of p is equal to c minus c into price into slope. Yeah. Okay. So this was your basic linear demand response curve. So the curve is linear. That is what we are given. So now the question is, if I want to model this curve, I have to create a model. Only then I will know what is M, what is C, so on and so forth. So what will happen? I will be using a technique known as the simple linear regression. Okay, SLR. This method will be used to identify this type of a curve. So a general SLR model is nothing but y hat is equal to beta naught plus beta 1 x, right? Beta naught hat, beta 1 x. This is the SLR model. Or in more generic terms, it is basically y is equal to beta naught plus beta 1 x plus epsilon. This is the general version. Okay, so that is the SLR model. Y hat is equal to beta naught hat plus beta 1 x, or in general, y is equal to beta naught plus beta 1 x plus epsilon. So this is going to be your basic version. I hope all of you are familiar with this particular up to this point. You have studied, right, SLR? Yes, no?
Yes, sir.
Yes, sir.
Okay. So we have studied SLR. Now the question is, how do you identify B? How do you identify? Okay, before even that, this and this are very similar, right? When y is equal to demand at the price point P, when x is equal to price, beta 0 is equal to C, and beta 1 is equal to minus M, this model and this model become equivalent. So if I take demand as my response and take price as my independent variable, I can basically fit a linear demand response curve using the method of SLR. So that is the first business application of the model. Now the main question comes. Okay. Now the main question comes, how do you find out finding beta 0 and beta 1? So how do you find out beta 0 and beta 1? For SLR, do you know what is the best value? Do you know the formula for finding beta 0 hat, beta 1 hat? What is the best estimate for beta 1 hat? Any idea of the formula? Okay, let's look at this. How is an SLR different from a straight line? How is a simple linear regression different from a straight line? This guy and this is a straight line. What is the difference between the two?
The points are not only on the straight line, they are around the line.
How do you know that?
Uh,
Which
because
term in this tells you that?
yes, because there is an error vector there, which I mean, which has in order to make it a straight line, it has to be 0.
Super. So exactly. So when you look at a graph, let's say I draw a graph. If all the points lie on this line, if that was my data, then a straight line model will work. But unfortunately, how does my data look like? It looks like something like this. They don't lie on a straight line, but they lie around some straight line. So some points will be above, some points will be below. They lie around some straight line, right? So the objective is to find the best fit line. Okay, so given a data, I want to find the best fit line. So how do I find the best fit line? What is going to be my primary concern? What is going to be my primary concern that drives this best word?
Reducing the error.
It is there, exactly. So it is the epsilons that are there. So what is an epsilon? This is my predicted point. The black dot is my predicted point, and this distance between the black dot and the red dot is the error. Here is 0, here is something, here is 0, here is something, right? So I have E1, E2, E3, E4, so on and so forth up to En. And now best fit line should do what? It should reduce these errors. I cannot individually reduce all of them. So what do I look at? I look at the average error. On an average, what could be my best error, best fit line? So that the deviation is around that average point. So whenever you fit a best fit line, you are basically looking at some average line such that the total variability around these points, total variability of these points around the line is minimized, right? So it's basically some average line that sits there so that the total variability of those points are captured as much as possible. So that's what drives it. And the method that is used there is something known as least squares method. We are not worried about that. But when you look at a simple linear regression, there is a beautiful formula for beta 1 and beta 0 based on the least squares technique, right? So beta 1 is nothing but, I don't know if you have come across this, but take it down, summation xy minus n into x bar y bar by summation x squared minus n into x bar squared. So what is the product of x and y total data differences with n into x bar y bar, the mean of x bar and the mean of y bar, divided by what is the square of my square of my independent variable minus n into x bar squared, right? So that is going to be your beta 1, and your beta 2 is y bar minus beta 1 at x bar. Okay, so these two are the formulas, right? So this is how you get the beta 1 and beta 0. You can find similar versions for beta 2, beta 3 MLR, not right now, but they are also there. But remember beta 0 and beta 1. Okay. Now comes a very
So,
interesting
sir, for the exam, do we have to memorize these?
yeah, this formula is basic. Yeah, this formula you should know.
All right.
This formula you should know, right? Sometimes we ask, sometimes we don't, but this formula is basic that you should remember. Okay, right. So finding beta 0, beta 1. So given a data set, you will find beta 0 and beta 1. All of you with me so far? So if I give you a data set, if I have x, y, let's say I have data point 1, 2, 3, 4, 5, and the corresponding y is let's say 100, 120, 90, let's say 85, then 100 again. So xy is nothing but 100, 240, 3 9 are 27, 274, let's just take it as 84 is 32, and 500. Sum of these guys is xy. So when you sum these up, this becomes xy. The average of this column is x bar. Average of this column is y bar. So just substitute all of these numbers over here. You'll get the numerator. Square 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared is x squared minus n into x bar squared. That will give you beta 1, and then you'll get beta 0 as y bar minus beta 1 into x bar. Okay? Right, super. Now what you can do, given a data, you can fit an SLR. You will be able to find the demand response curve. Let's say the x was your price and the y was your demand. You can find the demand response curve. That is done. The question is, when you fit a model, what is your goal? When you are fitting any model, what is your goal?
To have a minimum error.
You find a minimum error. When will you get minimum error? You have error measures, you can calculate the error, but how do you know that that is the minimum possible error?
I mean the line is very close to the points, or
What does that mean? When the line is very close to the point, what does that mean?
That we have found the
The
best.
error is negligible.
You have found the best model, and the other person was telling something.
That it is the best fit line that we have found.
How can you tell me that?
Based on the errors, the reduced errors.
Do you tell that I have an error of 10, so it is a best fit model? Someone could tell you, why is it that the best fit model? What do you say? What do you say when you have this model? I have a model for price and demand. In our case, it's price and demand. X is price, Y is demand. When you say that this model is good, when you say that the error is 10, only 10, no? Do you say based on error, or do you pick a model based on error? But you represent the model or tell about the model in terms of what? The demand, is it constant or is it changing? 100, 120, 90, 80, 100. Is it constant or is it changing?
Changing.
Okay. When something changes in statistics, what is the name that we use? We don't use change. We use the word that starts with V.
Variability.
Variance.
Say it is variable, right? So the demand is variable. So how do you say that my model is good?
If the variability is very low.
When the variability is very low?
Yeah, so we say that it is a good model when we can observe that the demand is going down as the price increases. So they are correlated. We establish a correlation between the two.
Okay, you establish a correlation, but then what do you say? Do you say that they are correlated, so it's a good model? They are highly correlated. Let's say the thing is very highly correlated, so it will be a good model. It will be a good variable to take. But how do you know that it's a good model? What do you say in terms of variability?
Variance are same.
Variance are same. No. You say how much
Variance is
amount?
low. Variance is low.
No, you don't say variance is low. Variance depends on the data. You say how much amount of variability in Y is explained by X. So if the variability in Y is 100%, it is variable. Of that 100%, I am able to explain 90%. Then it is a good model. Whether 90 is good enough or the best, that is a different debatable issue. But you say a model is good, then there is a significant amount of variability in Y that is explained by the model. Correct? So if I fit a model between price P and demand D and get a model which is explaining only around 20% of the variability, which it indirectly means that P and D are not correlated. That is okay. But the model is bad because it's only explaining 20%. However, if some other model, let's say it explains 80%, then it means that that model is good. Right? Correlation only tells you what variable to be taken. After that, how much it explains is a different question. Correct? So that is how you build models. You want to build models such that you are able to capture the maximum amount of variability in the dependent variable, which is Y. Okay? All of you with me?
Yes, sir.
Yes, sir.
Okay, super. How do you measure variability? In ANOVA, you have all, in fact, we will be seeing this in the course also. What is ANOVA? Form for this guy. What is the full form for ANOVA? No one. All of you use ANOVA, but no one knows.
Analysis of variance.
Analysis of variance. Super. So this is known as ANOVA, analysis of variance. Very good. So you are going to analyze variance, which means there are three types of variability that happens when you fit a model. There are different types. There are basically three. What are they? In an ANOVA table, what are the different rows? You have an ANOVA table. In the first column of the ANOVA table in Excel, there will be three names written. What are they? What are the three names that would be written? Come on guys, you should be seeing those videos. It will appear in all videos whenever you put an Excel.
So could you repeat your question?
My question is, you are going to measure variance, okay? When you look at variance, you are going to basically look at this model known as ANOVA, ANOVA, which stands for analysis of variance, which means you are going to analyze variance. And when you do an ANOVA model, there will be three rows in that model. What are those three rows that you see? For example, when you fit an SLR in Excel, you will get three rows in the ANOVA table. What are those three rows? What are the titles for those three rows?
sum of squares. There is one.
That is column number 2. That is column number 2. SS is column
Right,
number
right,
2.
right.
What is the first column? The three entries.
Within. I think it was within, between, and total.
It is regressor, residual,
Right, right, right.
and
That's
total. These are the 3 different variances that you see in an ANOVA table, which is the regressor, the residuals, and total. And they tell you whether the model is good or bad. Right? Okay. Now let's look at ANOVA table. So in ANOVA table, you basically have 3 rows. The first row corresponds to the regressor. The second row corresponds to the residual. And the third row corresponds to the total. So this is an analysis of variance table, which means that once you fit a model, there are 3 different types of variances that occur. The first variance, let's take the last one, is the total variability. Given this data set, what is the total variability in the data set? That is what is total. This is nothing but total variability in the data. Right? So that is going to be the bottommost column. How do you calculate variance for any data set? How do you calculate variance? This is also known as SS, right? How do you calculate the variance? What is the variance? Let's start from that. What is variance? Come on, guys, you have to answer. Only if you answer, I can give you the solution.
Is it the average deviation? I mean, squared deviation.
You're right. What is it in one word? The mean is this. The variance is this. Mean is dash moment. The variance is dash moment. Mean is the first moment. The variance is the second moment. Right? So it is this guy.
Yes,
the total variability is nothing but I have a data set which has n data points. I is equal to 1 to n. How much are they all deviating as compared to the mean? So yi minus y bar, the whole squared, summed up over I is equal to 1 to n, is the total variability available to me in the data set. Right? The total variability of y. So if I have a data that looks like this, let's say I have y, this is y1 to let's say yn, y1, y2, yn. The mean of this guy is y bar. So the SS total is nothing but y1 minus y bar squared, y2 minus y bar squared, so on, yn minus y bar squared. Sum up all of this, that is your SS total. That is your total variability that is available in the data. This is what it is. 5000 is my total variability. That is what your bottommost row of your ANOVA table tells you. Okay. Now let's say you fit a model. You use some X and then you fit a model, you will get a Y hat. For every Y, you will make a prediction, which is going to be Y1 hat, Y2 hat, so on and so forth, Yn hat. Then what is the error, sum of squares of errors? What is the error at this point between Y1 and Y1 hat? What is error? What is error? How do you calculate error?
y1 hat minus y1 whole square.
No, it is always actual minus prediction. So Y1 minus Y1 hat is your error, and we want sum of squared errors. So this will be square. Okay, always remember it is actual minus predicted is your error, because you have error measures like MAD, MFE, MFE, MAP, MFE, so on and so forth, which are dependent on sign, tracking signal, so which are dependent on sign. So always remember error means actual minus predicted. When you square it does not matter, but that is the definition. So you do this y1 minus y1 hat the whole squared, y2 minus y2 hat the whole squared, so on and so forth. Sum this up, this becomes your sum of squares for error. Summation I is equal to 1 to n yi minus yi hat the whole square is the total variability that goes to the error. So SST is 5000, say it is 5000. Out of this 5000, the errors are taking, let's say 2000. Okay, so of the 5000 total variability that is there, 2000 has gone to errors. Which means what happens to the remaining 3000? What happens to the remaining 3000?
They are attributed to the regressor.
Which means what? It is captured by the model, right? So the remaining 3000 go to the regressors, which means the regressor price that I have used to model demand, which is D, is able to capture 3000 out of the 5000 variability in D. Making sense? That is why this is known as analysis of variance. You are basically checking of the total variability, how much is accounted for by the regressor, how much is unaccounted by the regressor. Okay? Yes, no?
Yes, sir.
Okay. So the regressor variability, you can basically take it as SST minus SSE. This is basically error E. This is basically total T. This is known as SSR or sum of squared regression. Okay, SST minus SSE. Or what I can actually do is, for the regressors, I can sum up something and get the SS regressor. What do? I take the difference between y bar for the data and yi hat. So y1 hat minus y bar the whole square, y2 hat minus y bar the whole square, so on, yn hat minus y bar the whole square is your sum all of these up, that is your SSR. So SSR is equal to summation over I is equal to 1 to n yi hat minus y bar the whole squared. Okay? All of you with me? This is your SSE. This is your SST. All of you with me so far? Yes, no?
Yes,
Yeah.
sir.
Super.
Yes, sir.
So this is basically column number 3 in your ANOVA table. What is column number 2? Column 1 will be your name. Column 2 has something. Then you have column 3.
So column 2 will be degrees of freedom.
It will be degrees of freedom. Super. What is the total degrees of freedom for my model? What is the formula that sits here? All of this is basic stats. Okay, we are running out of time. Let me just write it down. So this is going to be n minus 1. This is going to be number of predictors, right? Usually this is called k, number of predictors. Yeah, and the error degrees is n minus k minus 1. That is your error predictor. So if you add up all these, if you add up these two, you will get SST. Always remember, in the ANOVA table, whenever you add up the regressor and the SST, you will get the total. So K n minus k minus 1 plus k is equal to n minus 1. That is why this is n minus 1. SSE plus SSR is equal to SST. That is what is this number that you will get, right? So this is in the ANOVA. Super. Now you have told me that out of 5,000, 3,000 variability you have explained. Okay. The question is whether the 3,000 is significant or not. For you, 3,000 may be okay. For me, it may not be okay. So how will we justify? We will do a hypothesis test there. So we basically do something known as the F test to see if the model is significant, right? So I would compute something known as the F statistic, which is nothing but the mean sum of squares of regressor by mean sum of squares of error, right? So that is going to be your this thing, F statistic. How much amount of variability on an average sitting with the regressor and how much amount of variability on an average is sitting with the error. And if this number, the larger this number, the better the model, right? So this is going to be your MSR by MSE. So what is MSR? MSR is nothing but SSR by K is degrees of freedom by SSE by degrees of freedom for error, which is n minus k minus 1. So on an average, if I give you k degrees of freedom, you are able to capture SSR amount of variability. So SSR by k is the mean variability captured by the regressor. If I have n minus k minus 1 degrees in which I can move, my errors can move, SSE is the amount of variability that they account for. So SSE by n minus k minus 1 is the mean amount of errors that is given that is captured by my error. The ratio of these two is my F statistic. Larger F statistic implies good model, right? How? Because this is a hypothesis test where you have a H naught and a HA. What is the hypothesis of an ANOVA? Null hypothesis of the ANOVA. I've given you this clue. Larger F statistics means good model, which means what? What is H naught?
H
And
naught
your
is that the model is good and it returns the best fit line.
no, that is not H naught. It's actually the opposite. So when you look at the F statistic, it will be something like I'm not exactly good with this diagrams. It has 2 degrees of freedom, but it will be like this. Okay, this will be 0. It will be a positive curve because MSR and MSE is always positive numbers because we are variance. So it will be a positive skewed curve. So 0 is where it starts. It goes up to, let's say, infinity. You are having a cutoff value at this point. So larger F means this is the rejection area. This becomes your rejection region. So when I say good model, I must reject H naught. What is happening? Sorry about that. Yeah. So when I say good model, I must reject H naught. So H naught in regression basically means the model is insignificant. Which is nothing but beta 0 equal to beta 1 equal to 0, since this is an SLR. For an MLR, I'll just write it because it will come later. For an MLR, it is nothing but beta 0 equal to beta 1 equal to beta 2 equal to so on up to beta k is equal to 0. All betas are 0 is your ANOVA test. Given k predictors, because remember, it is always given k predictors, how much variability I am capturing. Even if one of them is insignificant, the model will become insignificant. So all of them should be non-zero. That is the question. And your alternative is that the model is significant. Which means at least one beta is not equal to 0. So even if one beta is not equal to 0, you will say I am able to capture something significant. So the model is significant. If all of them are 0, you will say the model is not significant. Okay? Yes, no.
Yes, sir.
Okay? So this is very, very important to note. Super. Now all of this is fine. Ultimately, when you do regression, what is the most important guy that you look at? The most important parameter that you look at. You fit a model in regression and then you compute this guy. Who is he? That one letter parameter.
Are we talking about R squared?
Exactly. So we can calculate something known as R squared. What is R squared? Go back to my starting thing. What is our goal? To build a model that explains the variability of y, right? So what does R squared tell you? What does R squared tell you?
That how much of variance can be explained by the
Exactly. It is nothing but percentage of variability in y that is explained by the model. Right? So that is your R squared. That is why when you fit a simple linear regression or an MLR, you report the R squared, which will tell you I have fit a model with R squared of let's say 82%. It means 82% of the variability in Y is being explained by your model. Super. So how do I calculate this guy? Looking at the ANOVA table now. Looking at the ANOVA table, if I want to calculate R squared, what is the formula that we use? Percentage of variability in Y explained by the model. So what is the variability in Y that is explained by the model from the ANOVA table? Which term gives you that?
SST.
SST. SST is the total variability in Y. How much of that is explained by the model?
SSR. So
SSR. Exactly. So I have a total variability of SST. Of this, SSR is explained by the model. So your R squared is nothing but SSR by SST. Right? Which is equivalent to saying, what is SSR? SSR is nothing but SST minus SSE by SST, which is nothing but 1 minus SSE by SST. Okay? So this is what your R squared actually means. Of the total variability, 5000, how much is explained by the model? 3000 is explained by the model. So 3000 by 5000, 3 by 5 is basically your this thing. 60% is the amount of variability in Y that you can explain using the variable of price. That is what you say. Then you go and check, okay, I make this claim, but is the model significant? Can I, just because it explains 60% does not mean that the model is significant. That could have been random luck. So how do? You go check the F statistic. So the F statistic will tell you whether all the betas are zero or at least one of them is non-zero. So you do a check. Once you do a check, you will then get to know, okay, the model is significant or not significant. Let's say the model becomes significant, which means what? At least one of your betas, in our case it's SLR, so either beta 0 or beta 1 is not equal to 0. That is what you conclude. So using ANOVA, you will reach at this point. The next question is, okay, beta 0 or beta 1 of them is not 0, but are both of them not 0? Right? So to check whether both of them are not 0, you will then go to the below table in your Excel, which will basically be the t-test. Right? All of you with me so far, are you able to understand the thought process that I am telling you? How do you look at the table? Interpret the values?
Yes, sir.
Any questions? Just look at ANOVA. From the ANOVA table, you get your R squared, you get your model significance. Once your model becomes significant, then you go to the t-test to see which all betas are significant. Okay, this is the thought process. Any questions? No questions. Okay. Then for your t-test, what you get in the t-test table of Excel. What are the two rows? Let's say you are building an SLR. What are the two rows that will come?
Intercept and the coefficient.
Super. You will have the, in fact, the first thing will be intercept. And the second thing will be the coefficient. So SLR, the intercept represents beta 0 and the coefficient represents beta 1. Right? You will get their values. First thing will be their values. The second column will be what? The second column will be what?
Standard error.
It will be the standard error. Why? Because they are estimates. This value is the estimate for beta 0 hat. This value is the estimate which is beta 1 hat. Each of them will have a standard error for beta 1, standard error for beta 2. After this is where you will have the t statistic. Right? The t statistic is nothing but beta 0 hat by its standard error and beta 1 hat divided by standard error. Sorry, beta 0 and beta 1. Super. Once you get a t statistic, it means it is a t-test. What is the null hypothesis? What is the alternative hypothesis? What is the null? What is the alternative? In your Z test, T test, what is the null? What is the alternative?
So will null hypothesis be the model is insignificant?
Exactly, not the model but the coefficient. The null hypothesis is that beta equal to 0. In this case, beta 1 equal to 0. Sorry, it is beta 0, no? Beta 0, beta 1. In this case, it is beta 0 equal to 0. And in this case, it is beta 1 equal to 0. That is your null hypothesis. That the beta is 0. So what happens in the F now, when you look at model significance, here you take beta 0, beta 1 equal to 0. You check for both. Even if one of them is not 0, the model will become significant. Now you come down and check for each of the betas. Beta 0, whether it is 0. Beta 1, whether it is 0. You do an individual t-test for each of them. And then you see which betas are significant. Right? So that will be your second, that will be your H0. After this, what you will have two more columns. What are they? What are they? After this, in your this thing, in your ANOVA, you will have two more columns. What are they? You'll actually have four, but they are just repeat of the same thing.
So one is p-value. I mean one column.
So p-value is given. Oh, okay, so you'll have p-value. Then you'll have three. One is p-value. The other two are
lower 95% and upper 95%.
You have a lower 95%, upper 95%. What are they? Lower and upper 95%. They are nothing but the
alpha.
No, alpha is 5%.
Acceptance.
Okay. Acceptance level is 5%. What is the other name? alpha 5% implies dash 95%. Implies a 95% dash. Let's like to see that.
Confidence in
Exactly.
confidence
So
in
95%.
confidence.
This is a 95% confidence interval. Okay. So you construct a confidence interval. Let's say I'm not giving you p-value. I'm not even giving you the test statistic. I'm giving you only the only the confidence interval. Let's say the confidence interval for beta 0 is -1 to -2, and the confidence interval for beta 1 is nothing but, let's say, 2 to 4, for example. Then in this case, will you reject H0 or do not reject H0? Reject or do not reject? How do you tell? You are given two numbers, -1, -2, 2 and 4. They are your confidence interval for intercept and confidence interval for your coefficient. Will you reject H0 or not reject H0? And the H0 is that beta is equal to 0. What will you do? Since I've already explained p-value before, I'm doing confidence interval this time.
So for beta naught will fail to reject the H naught, but
Okay.
for beta 1 will reject the H naught.
Why?
Because the value
Value?
because values for beta 1 are high, so that probably means that there is at least one or more which are non-zero.
No. No, it does not. So
Okay.
what happens? Look, you interpret a confidence interval like this. If the confidence interval contains the hypothesized value. If the confidence interval, in fact, let me put it in this sense. If the confidence interval contains the value 0 in our case, then reject. Then do not reject H0. Why? Because you are making the assumption that beta is equal to 0 and doing all the computations. How do you construct a confidence interval? You construct a confidence interval based on using beta 0 hat. Beta 0 plus or minus standard deviation, plus or minus the standard error gives you the confidence interval. Right? Plus or minus z times the standard error gives you the confidence interval. For example, for a Z test, how do you create the confidence interval? Confidence interval is nothing but x bar plus or minus sigma into z. This is your confidence interval, right? This gives you the from the sample. You have taken the sample, built an interval around that, right? The 95% or something comes from the z value. So z value of for the 95% value, you will get the 95% confidence interval. Now what happens? Using the sample, you have built a 95% confidence interval. If that confidence interval does not contain the hypothesized value, which is mu is equal to 0, if this value is not present within this guy, then what does it mean? The x bar is true, the sigma is true, the z bar is true. So the only thing that cannot be true is this guy. So if it is present, that implies you do not reject. So similarly, if the confidence interval contains the value 0, you do not reject. If it does not contain the value 0, you have to reject, right? Because from the data you have computed beta 1 using those formulas, which are all valid. From the data you have calculated the SE, which is valid. From the data you have, from your type 1 error, which is a 5%, you have calculated 95% confidence interval. This is also correct. So only thing that is wrong, it is the assumption that beta is equal to 0. Right? So beta is not 0. So in this case, -1 to -2 does not contain 0. 2 to 4 does not contain 0 because lower bound is 2, upper bound is 4. Lower bound is -1, upper bound is -2. So in both cases, the 0 value is not contained. So both beta 0 and beta 1 are significant. But let's say if this confidence interval is something like this, -1 to +2. Now is beta 1 significant or not significant?
It contains 0.
It contains 0. So it is
Significant.
It is significant. It is not significant because significant means beta is equal to 0. No? It is not significant because beta becomes 0. Okay? So here that terminology is varied, but all you can say is when it's between -1 to +2, I am going to reject H. I am not going to reject H0. Do not reject H0 and conclude that the beta value becomes 0. Okay? All of you with me?
Yes, sir.
Yes, no? Okay.
Yes, sir.
So this is basically your SLR.
If we have 0, then we do not reject H0, right?
Yes, if you have 0, do not reject H0.
Okay.
If the confidence interval contains 0, then do not reject H0. Okay. So this is true for any confidence interval, 95%, 90%, 85%, whatever. That percentage depends on your alpha. The alpha is depending on your type 1 error, type 2 error. Okay. So this is how you interpret a SLR model that you build using Excel for a data set, and when you can use SLR for a demand response curve which is linear in nature. Okay, I will stop here for today. After this would be your syllabus for your quiz which is happening on Sunday. A point to note, the TAs will be doing a session tomorrow. Okay, TA session is preponed to tomorrow.
What time, sir?
Tomorrow 5 to 7, same time.
Okay.
This time is the same. It is just being done tomorrow so that you get the weekend to prepare. So they are doing it tomorrow. So there will be no session, no TA session on Saturday. I think the date is 22nd. So no TA session on Saturday. Your quiz one is on Sunday, which is 23rd of February. Please check your grading document. You have to get a course grade. You have a minimum score that you should get in your quiz 1 and quiz 2 put together. Alright. So make sure that you attempt both the quizzes. Do not miss any quiz. It will become very difficult for you to get a course grade. So make sure that you take both the quizzes very, very seriously. Immediately after the quiz, next Tuesday, which is nothing, which is on 23rd, 25th, right? 25th, that session we will discuss the quiz. We will discuss the quiz. Any doubts that you have, you can come. This session will not be recorded, will not be streamed. right? So in that session, if you have any doubts in quiz, you will come and ask me. We will do that session, and only after that we will sign off the quiz. There will also be a discourse post which will be taken where you can raise any concerns that you have. But please wait for the answer key to be released on Monday. Take your time, go through that answer key, then raise the questions in discourse. All right? Because if you raise based on your memory, someone else will panic, thinking that they have done some errors. So please be considerate. Raise your questions after the answer key comes. If there is any error, we are always here to rectify the error and give you the benefit, right? So just make sure that you wait for the answer key and do join the quiz on the 25th, where we will discuss quiz 1. So as long as we discuss quiz 1, the session will not be recorded or streamed. If there is no discussion, we will start off with week 5 content, which for which the session, after which the session will start recording. Okay, only the quiz discussion, we want you to come and interact with us, so we don't record that session. Okay, all good.
Okay, so tomorrow's session will be a revision session or what?
Yeah, the TA is basically do a revision session tomorrow.
All right, sir. Yeah. Thank you.
Yeah, thank you.
Tomorrow's session will be recorded, no? Tomorrow's session.
Yeah, that will be recorded. Yes.
Okay. Thank you.
Okay. So this is what I had for today. Yeah, we have only 4 of us here. Any doubts you can ask me, or we can meet next week.
Sir, just one doubt. Actually, in week 3, under TA session, I had one doubt. If I just a minute. Can you just open this post? I sent you the chat.
Yeah. Okay. One second. I have to use my ID. Copy link address. Okay, degrees of freedom. Yeah, this is 3 ma. Yes, it's 3. It was changed later.
So actually, your screen is not visible. It is the.
Oh, that is okay. No problem. The discourse that you have shared, the answer there is 3. It was changed later after the live session. I forgot to update this thing. The TA has now updated it. The
No,
answer
sir,
is 3.
no, the answer was fine. Actually, I was asking that I posed the doubt. I didn't get that. Why in the first question, in the third question, which I said send, there sir has considered the parameters, and in the next in the following down the question, there is a one more question. There they didn't consider the parameters. So I was actually in doubt that why when we have to consider the parameters and when we have to not. So if you
So
can
in the RO filter question, what would have happened is we would have specified the lights that you will have to use. Okay. So which means the frequency table that you will have to develop already tells you what are the bins.
Okay.
Right? Whereas in the second question that you are referring to, it's a different question. It's not the same question. It's a different question. In the second question, we have only given you the sample data. From the sample data, you will have to create the bins with the assumption that the days are taken as the bins. Okay, so once you create those bins, you are basically assuming the basically from the sample you are calculating the, if it's a uniform distribution, I don't know what distribution it's, normal distribution. So if it's a normal distribution, from the sample you will have to take the mean and you will have to take the standard deviation to get the PMF, so on and so forth, right? So in that case, the 2 parameters are computed from the sample. So P is equal to 2. Understand the difference?
Okay.
So check the question.
Yeah.
Check the question. Now go back and check the question. In the RO filter question, we would have given you what should be the life band that you should take.
Yeah.
Whereas here, we are not telling you the life band. We are telling you take days as bins, build it. Which means what? After taking days, you will have to then go and compute the mean value, the standard deviation, compute the PMF, so on and so forth. That is why what we are doing is, we would have asked you to assume that it is following a normal distribution where days break it into equal areas. Just make that assumption and do. So that is why you are basically calculating the two parameters from the sample.
Okay.
Okay?
Yeah.
Making sense? So whenever you calculate any parameter from the sample, those many degrees of freedom will be knocked out. That is why here it is 2. Whereas in that problem, I have already told you what distribution it is. It's, the range is given for uniform. So there is no parameters you calculate from the sample. So that is, there P is 0.
Okay, sir, got it. Yeah.
Super. All right.
Yeah. Yeah. Thank you, sir. Thank you so much.
All right. No problem.